in 2D we have choices, right? And the most common choices are triangles and quadrilaterals. Yeah. So we'll start by looking at a constant strain, what we call a constant strain triangle. And even though, so we call this CST, this has 3 nodes. So even though we call it a constant strain triangle, in this problem, it's a scalar problem. There's nothing to do with elasticity or strain. We still call it a constant strain triangle. And the reason is because it's basically only capable of modeling constant fields. So in an elasticity problem, once you were to develop, what you would see is that, across the element, there would only be capable of interpolating or having a constant field across the element, right? Constant strain field. So we'll start with just a generic triangle with 3 nodes. X1, X2, X1, Y1, X2, Y2, X3, Y3. And then our displacement field or approximate field will be U of H equal to C1 plus C2 X plus C3 Y. And so another way, we had this X vector before that was like 1 X Y. So that is our interpolation. The way you would develop these, just like before, if we had U1, U2, U3 is equal to, now we're going to evaluate our X vector at each of the nodes, right? So 1, X1, Y1, 1, X2, Y2, and 1, X3, Y3. That's equal to C1, C2, C3. And then we can get our shape functions by N equals X transpose times A inverse, where this is A. So it's no different than what we did in 1D. And let's look at an example. We'll do it in Mathematica like we did before. So we have a triangle that has nodal locations 2, 1, 5, 3, 3, 4. And really soon, before the end of the class, we're going to introduce node numbering schemes. So I'm going to number on the inside of the triangle the local node numbers. So in this case, there's only one element. We'll see in a second how when you begin to assemble elements that you can have local node numbers and you can have global node numbers, right? In this case, there's only one element, so the local node numbers are the global. But we'll call this node 1, this node 2, and this node 3. And the point is, just when we assemble our A matrix, we need to do it in the order of our node numbering scheme. Okay. All right, so just like we did in 1D, we'll have, blow this up a bit, x equals 1, X, Y. A is going to be equal to x evaluated at, this time we have to evaluate it at x, which in our problem is 2, and y, which is 1. And then evaluate x at x equals 5, y equals 3, and x, where x is 3 and y is 4. So then we just have x dot inverse a, and those are our shape functions for this element. So there's three nodes, there's 3 shape functions, and that's what they are for this particular problem. Right? Now, you may already kind of see an issue that we won't really have a solution with until either next class or the class after. But as we're doing things now, we have to basically create a new shape function matrix for every element. Every element, because it's a function of the nodal coordinates, right? The global, in physical space, the nodal coordinates, you have to put those in to get the shape function matrix. So basically, as things are done, you would, you need different shape functions. Now, we did see before, if all your elements have the same volume, like even in the 1D case, right? We were doing the same thing. We were assembling the element shape functions element by element, but when you integrate them to compute the element stiffness matrix, then they all end up, as long as they have the same shape, you end up with the same element stiffness matrix for every element, right? Type. And that would be the same here. If you had a whole bunch of triangles that were the exact same shape, same base and height, ultimately you would have the same element stiffness matrix when you do the integration, because you're integrating over the length and the x and y. So the integration would result in the similar element stiffness matrices. But as we're doing things right now, you need a different shape function matrix for every element because it's functions of the global coordinates. Okay? Obviously that's not an optimal way to do things. So we'll see how to fix that later. And it's really clever. All right, so we'll just talk about a couple of other 2D element formulations. We won't go through all the details. So we can have a linear rectangular element. This is typically called quad 4. So for this, we will introduce a local element coordinate system that sits in the lower right-hand corner of the element, lower left-hand corner. So we'll call this x bar and this y bar. And so this element has a height b and a width a. And local node numbers 1, 2, 3, 4. And so the displacement field we will use for this problem will be C1 plus C2x, I said displacement field, approximation field, And I'm just going to write down what the shape functions are in those element element coordinates. So it's 1 minus So those are the shape functions. You develop them the exact same way. We could also have quadratic triangle. So here we have 1, 2, well, let me put them on the inside. We have 1, 2, 3 corner nodes, and then we also have mid-side nodes 4, 5, and 6. And so the approximation field for this element is so you should see we basically have the same amount of terms that we have node numbers, right? And again, we're pulling them from that, remember the Pascal's triangle that I drew last time? Basically, they have to go in order from the Pascal's triangle and be symmetric. So I'm not going to write down the shape function for those because we know how to do that. I'll go ahead and basically also just write down a quad 8. So that we have the node numbering scheme. So for this we'd have 1, 2, 3, 4, and then mid-side nodes 5, 6, 7, 8. And notice how they're labeled corner nodes first, so that the node numbering corresponds to the quad 4 where the corner nodes are, right? And then as we add new nodes, we label them. So in this case, we have approximation field that. Now, we could also add one element right to the center. This is called a, I don't know where the name comes from, but these are known as serendipity elements. I really don't know where the name comes from, but those are named called serendipity elements. And you would obviously have the term that completes the Pascal triangle, right? So that's the C9 x squared y squared. Now we'll get into it next week, but I think I might have mentioned. Let's see here. If we're gonna I want to go too far aside and not finish what I want to finish today, but remember when we derived the polar elasticity equations? One of the reasons I wanted to do that kind of long derivation was to show you. Remember how when we introduced the P, we introduced it as a Lagrange multiplier, right? Remember, it turned out to work out to be like a thermodynamic pressure, right? When you just turn the crank on Hamilton's principle, but we introduced it as a Lagrange multiplier. And it is a Lagrange multiplier, and it turns out in that case you can eliminate it by introducing the thermodynamic definition, or using the thermodynamic definition of pressure. But if you assumed that the constituents were incompressible, then you couldn't not do that. It would not fall out that way, and you would see basically clearly that P is a Lagrange multiplier always. And you have to eliminate it from the equations by solving for it. Anytime you have a Lagrange multiplier in a problem setting like that, you end up in typically what's called a saddle point problem, right? So you're trying to find a solution that's neither a maximum or a minimum, but it's a stationary value, right? And those are very, very tricky, because if you're not close to it, you're just going to shoot off to the nearest maximum or minimum, right? It's very hard to converge to a saddle point problem. And so there's all kind of unstable situations you can get yourself into numerically when you're trying to solve those problems. And so what that means for us, or what we'll see next week, is that if you try to solve the polar elasticity equations, right? So remember, in that setting, they're coupled, they're mixed, right? So you have like a scalar field problem in the pressure, and then you have a displacement field in the conservation of momentum for the displacement, right? And because of that coupling, if you use equal order interpolant elements, so if you use, say, quad 4 for the pressure and a quad 4 for the displacements, you'll end up in what's called it violates something called the imp soup condition, and it is proven to be unstable. Okay, so one way to correct that is to use unequal interpolated elements. So you could use a quad 8 for your displacements and a quad 4 for your pressures. So you're going to have quad 8, you'll have like basically quadratic interpolation of the displacement field, and then you'll have bilinear interpolation for the pressure field, right? And those are called Taylor-Hood element formulations. And again, this is where, as I was mentioning kind of at the beginning of class, some of the bookkeeping becomes really tedious. Because now, if you have quad 8 in your displacements, right? So there's no 9 there, right? Quad 8 in your displacements, and you have, right? So every node has two unknowns, right? Ux, Uy, Ux, Uy, Ux, Uy at every node. Then you have a quad 4 for your pressure field, but only the corner nodes have pressure unknowns, right? So your unknown vector looks like, at node 1, it's like unknown Ux, unknown Uy, unknown pressure. Same for 2, 3, and 4, right? But then at 5, it's only unknown X, unknown Y. Right? And so there's like and that's just for one element, and then every element has that, and you have to assemble the elements, right? So there's like a lot of bookkeeping you have to do, and this is where using some kind of finite element framework, all that's already taken care of for you, can really save you a lot of trouble.